share the screen. This is what I was referring to. So, what were you saying?
I don't remember if you did all of these, and then on the next page, and we or just take two out of three and accept it.
Oh, okay. I think I recall doing the first two on this page, right? So, what I'm gonna do is the third page. And this is where we get to, the whole importance of calculating the formal charges, right? In order for us to determine what the load structure is. Let me open this up here. Okay, so just to remind you of the formula for formal charges. Formal charge is equal to the group number minus half the number of bonding electrons minus the number of non-bonding electrons. So that's the formula that we're going to use to calculate the formal charges. So, the molecule that we'll be looking at is SiO2. Right? And we go through the same steps as we did for the others. We count up the valence electrons by consulting the periodic table. And in the case of silicon, its group number is 4. In the case of oxygen, its group number is 6, but because there are 2 of them, we have to multiply that by 2. So this gives a total of 12 electrons being contributed by the oxygen. So therefore, the total number of electrons will be 16 valence electrons, and I like to express it as pairs. So 8 pairs, and then we put the silicon in the middle, surrounded with the oxygens. So we start off with the bonding pair first, 1, 2, then 3, 4, 5, 6, 7, 8. All right. Then we calculate the formal charges. So for silicon, that will be the group number, which is 4, minus half the number. By the way, is this here in your way? On the screen?
Oh, I'm fine.
You sure?
Yeah.
Okay, all right. For the silicon, it's 4 minus half of 4 minus 0. So that gives you plus 2. And in the case of oxygen, it is 6 minus half of 2 minus 6 equals minus 1. So therefore, you're going to have minus 1 here, minus 1 here for the oxygens, and plus 2 here for the silicon. So what do you think is going to happen next? Based on what we did before. If I remember correctly,
Doesn't it takes one of the other one and goes to, because it's connected to one, so it's just to balance out power.
right, well, the charges will cancel, of course, but in this case, all of them. Because they have a negative charge here, on the oxygen atom, and you have a plus 2 charge on the silicon, what will happen is that this pair of electrons will come down and form an extra bond, right? The result of that would be that this negative charge will cancel one of the 2 plus charges. And then a similar thing will happen on this side, where this negative charge will cancel out the other plus charge. So the final structure is going to be and that would be it. So this would be the answer right here. All right. Okay, so that's basically how that is done. And this underscores, again, the importance of determining the formal charges, right? Because the formal charges helps to determine whether or not you're going to have multiple bonding taking place. All right. Any questions about it? Any questions? Any questions? Okay, what's next? So, before I forget, Ms. Fools told me that today, this morning, that there's an error, and she's correct actually. in one of the answers that I gave to the, a question in one of the past tests, which I posted in Canvas. So that's in reference to this particular test, number 3, spring 18, test, answer key. And it turns out that all this is wrong. This is actually possible in terms of the quantum law. N is equal to 4, then L can be equal to 3, and ML can be equal to -2. So please make a note of that when you're reviewing for your test, all right? Okay, so let me get out of this here. And go back to, okay, where am I going to go? Let me go to assignment number 9. Oh, by the way, so I don't know if I told you guys this, but the initial assignment number 9 I posted was not in the correct order in terms of the topics covered by the question. So I rearranged it and I resubmitted online. And I brought some copies here so that we can look at these questions together. Well, there's only 3 of you. So. And for you guys out there in Zoom, I'm going to, when I've just published it. So I'm downloading it now. Okay, so so okay, so let's start off with the first question. Well, what, let me switch this. All right, so the first question gives you the Born-Haber cycle for cesium chloride, right? And if you remember, the Born-Haber cycle is basically a stepwise approach of showing what happens when a metal and a non-metal come together to form an ionic compound, right? Go through different stages. You have the bond dissociation energy for the non-metal, you have the sublimation for the metal, and then you have ionization, electron affinity, and all that good stuff, right? And so this is it. And the question, well, there are several questions. The first of which is, give the name of the enthalpy changes represented by delta H1, delta H2, and delta H5. All right, so delta H1 is where we're going from cesium and chlorine to form cesium chloride. So what do you think the answer to that question is? What is the name given to that change where the metal and the non-metal react directly to form the ionic product? And feel free to look in your notes because we did at least 2 examples dealing with the Born-Haber cycle. So what do you think? And you guys out there in Zoom, please feel free to chip in as well with your responses. What's the name given to the enthalpy change where you go from the metal reacting with the non-metal to form your ionic product? It's called enthalpy of what? Enthalpy of what? Well, nobody remembers? It's called enthalpy of formation. Right, that's the enthalpy change, where 1 mole of a compound, in this case an ionic product, is formed from its elements. All right, under standard conditions, presumably. All right. Okay. What about delta H2? Now, if you notice in delta H2, you're going from cesium solid to cesium gas. Right? So what's the energy for that transformation? Going from a solid to a gas. What do we call that enthalpy? Enthalpy of does this look familiar? Sublimation. You're going from the solid state directly to the gaseous state, right? So that's enthalpy of sublimation. And then, scroll down here. Okay, delta H5. Great. So delta H5. Delta H5 is where you're going from the chlorine to the chloride. And of course, for the chlorine to go to the chloride, it must gain an electron. So the chlorine gains the electron to form the chloride ion. So that, what do we call this particular change in energy? When you have a gaseous atom gaining energy to form the gaseous ion. What do we call them? Okay, so that is called electron affinity. Does that sound familiar? Right? So that would be the answer that you would put here, right? For delta H5, that is the electron affinity, all right? So, as I said, when I introduced this particular topic, I said that most of the problems that you're going to encounter is where you have to determine the lattice energy. And the main reason why that is so is because the lattice energy is seen as a measure of how stable the ionic compound is. So the greater the stability, the more stable, the greater the lattice energy, the more stable the ionic compound is. Now, I seem to recall that when I introduced to you this concept of lattice energy, I said that in different chemistry textbooks and other sources, they define lattice energy a bit differently, right? Let me go back here. The cycle itself. Okay, so in some textbooks, they define the lattice energy as the energy change that takes place when the gaseous ions come together to form the solid. In other textbooks, they define it as the reverse, the energy needed to convert the solid to the gaseous ions, right? When I checked your textbook, it is the latter, not the former. In other words, the textbook says that basically the enthalpy, the lattice energy is the enthalpy change that takes place when you break up the ionic compound into its gaseous ions. So because that's what your textbook says, I'm going to stick to that, which means that I need to reverse this arrow to go from the solid to the gaseous ion, right? So this is what we need to find delta H 6 based on that definition, all right? So please remember the definition that we're going to use, because your textbook says so, is the enthalpy change that takes place when your solid is converted to your gaseous ions like this. In this case, it's the chloride and cesium ions. So basically, this delta H here is equal to the lattice energy, or delta H lat. In some textbooks that way. All right, so that's the definition that we're sticking to. Okay, so with that said, this is what we need to calculate. Let me make this small. Oh, not that small. Okay, so how are we going to calculate the lattice energy? Well, basically, based on how this cycle is arranged, if we start from the original elements, which would be the cesium and the chlorine here, what this means is that going in this direction here, if we add up all the enthalpy changes going in that direction, that would be the same as the enthalpy change going in this direction, all right? So basically what I'm going to do is start here and add up delta H 2, 3, 4, and 5. So I'm going to start off with 79 kilojoules per mole plus 376 kilojoules per mole plus 121 kilojoules per mole, and then minus 364 kilojoules per mole. And then I'm going to equate that to minus 433 kilojoules per mole plus delta H lat, which is what we're trying to find, right? So it's simpler arithmetic from here on. So what I'm going to do is add up everything on this side of the equation right here. So that would be 79 plus 376 plus 121 minus 364. And on this side, I got 212 kilojoules per mole equals to minus 433 kilojoules per mole plus delta H lat. And then to get delta H lat, all I have to do is add 212 kilojoules per mole plus 433 kilojoules per mole. And that's it. So 212 plus 433. And the answer is 645 kilojoules per mole. And that's basically how that is done. All right. Any questions about this one? Any questions? Any questions? Any questions? No questions? Any questions out there in Zoom? All right, so let me hear this. And let's move on to the next question. Go back to the original size. Oh, we're not finished with that question. There's a C part. Now the C part says, explain why the enthalpy change represented by delta H3 has a lower magnitude for cesium than for sodium. So what they're saying is, going back to the diagram here, for delta H3, which is right here, going from cesium gas to cesium ion, what they're saying is that if we had used sodium here instead, then what did the question say? Oh, so the question is saying that this here, delta H value is lower compared to if this was sodium, right? So if you replace cesium with sodium, then the delta H3 value would be greater than what it is for cesium, right? So the question is asking, why is that so? Why is it that cesium would have a lower delta H3 value compared to sodium? And remember, delta H3 in this context is the ionization energy. And we talked about the trends in the periodic table with respect to the first ionization energy as we go across a period and down the group, right? So the question is, why is it that cesium has a lower first ionization energy compared to sodium? Yes, sir.
Yeah, because it's lower in the group. So
Because cesium is lower in group 1 compared to sodium, and therefore what?
it takes, so cesium will take less energy.
Yeah, but why? Why is it that cesium, why is it easier for you to remove an electron from cesium as opposed to sodium? Right. Right, so therefore the distance, right, the core electrons, which I think is what you're referring to, will push away the valence electrons, or actually one valence electron away from the nucleus. So the distance between the nucleus and that valence electron will increase, and therefore it's easier to remove that valence electron from the cesium atom compared to the solar atom. So the answer to this question is, write it down here. The cesium atom is larger because the core electrons let me put it this way. There are more core electrons. That's what I should have said. There are more core electrons shielding the valence electron pushing it away from the nucleus, making it easier to remove. And that's it. That's pretty much the explanation right there. Oh, I wrote it in the wrong space. No worries. That's where it belongs. All right. So that's basically it. That's the reason why sodium has a lower first ionization energy compared to sodium. The sodium, cesium is lower in the periodic table. It has a larger radius because of the screening effect of the inner core electrons, and therefore it's easier to remove the valence electrons from cesium as opposed to sodium. All right. Okay. So that's it for number one. Number two, basically exercises in drawing Lewis structure. All right. Let me clear this here. So what I'm going to do, I'm not going to do all of this. I'm going to leave some of this for you to do, right? Let me do the first one, SCF2, right? So again, the steps that we talked about earlier, we're going to do the same steps. First step is that we go to the periodic table and we look up the group number for these elements. So in the case of selenium, that's 6. In the case of fluorine, that's 7, but we have to multiply by 2, so that gives you 14. So when you add this up, you're going to get 20 electrons, which will equal to 10 pairs, right? And then we put the selenium in the middle. We surround it with the fluorines. We put the bonding pairs, 1, 2, then 3, 4, 5, 6, 7, 8. So we have used up 8 of the 10 pairs. So the remaining 2 pairs will end up on the selenium. All right. And then we calculate the formal charges. So in the case of fluorine, the formal charge, oh, sorry.
That's right.
Will you use this, John?
That's all.
Okay, yeah, the desktop over there not working, so that's why.
That's fine.
Yeah, thank you.
Yep.
Okay, what was I saying? Oh, right. Formal charge. 7 minus half of 2 minus 6, and that gives you 0. And for the selenium, that would be 6 minus half of 4 minus 4. And that would be equal to 0 as well. So therefore, there are no charges in this particular molecule whatsoever. All right? And that's how you do that. Okay, any questions about this one? Any questions? Questions? Okay. Let me do carbon disulfide, and then, as I said before, I'm going to leave the rest for you to do. Okay, let me hear what you have to say about this one. First step. What's the first step? Okay, so carbon will contribute how many? What group is carbon in? 4, and sulfur will contribute how many? 6, and there are 2 of them, so that's 12. So when you add this up, total you're gonna get 16 electrons, which is equal to 8 pairs, all right? What's the next step?
Yeah.
Okay, so how do we place them?
Carbon.
Carbon in the middle?
And
Okay, very good, right. So the next step is to put in the. Yeah, but the bonding pairs first, right? So 1, 2, then 3, 4, 5, 6, 7, 8. Right, so I've used up all of the pairs. So the next step is formal charge, right? So remember, please remember this formula. Formal charge is equal to the group number minus half the number of bonding electrons minus the number of non-bonding electrons. That's a formula that we use to calculate the formal charge. So let's do so for carbon. So what's the group number for carbon? 4 minus half. What's the number of bonding electrons for carbon in the structure here? Remember, each line represents 2 electrons, right? So for carbon, what's the number of bonding electrons carbon has? 4, exactly. Minus the number of non-bonding electrons, which would be? Exactly. So this works out to be equal to +2, right? And then we do a similar calculation for sulfur. So what's the group number of sulfur? 6 minus half the number of bonding electrons. So what's that? What is that? 2 minus the number of non-bonding electrons, which is 6. So this equals to -1. So we have a +2 charge here, and we have -1 charges here and here, right? So what's going to happen next? Exactly. This will go here, this will go here. So the final answer is going to be double bond C, double bond S, and then 2 lone pairs there. And that would be the answer. All right. Okay, any questions about that? Any questions? Any questions? All right, so I'm going to leave the rest of that question for you to do. Let me clear this. If you have any problems while doing these problems, please feel free to contact me concerning that. You know what? Let me do this one, because this one is a bit tricky for you guys, because of something that I haven't told you guys yet. You know what? Before I do that, let me scroll down here. Okay. Let me go back to the PowerPoint and then I'll come back to that question. All right. In fact, that's the very same question here. Okay, come to think of it. So this question is asking for you to draw a plausible structure for the nitrate ion. So we go through the same steps as before. We start off with for the nitrate ion, we find the number of valence electrons. Okay, so what's the number of valence electrons for the nitrogen? Or what group is nitrogen in? Group 5. And oxygen is in group 6. And there are 3 of them, right? Now, that gives you 18. Now, here's the thing. We're dealing with a polyatomic ion here. And if you have a polyatomic ion, basically you need to add electrons if it's negatively charged, or if it's positively charged, you remove electron, right? Or you subtract electron, right? Now, in this case here, we have 1 electron, right? So that means that for the negative charge that is present, we have to add an electron to what we have already, right? So it is 5 plus 18, that's 23 plus 1, 24 electrons, which will be equal to 12 pairs, all right? So we put the nitrogen in the middle, surrounded with oxygen, right? And then we put the bonding pairs. Remember now, we have 12 pairs to assign. So we go like this, 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So the formal charge on the nitrogen is equal to the group number 5 minus half the number of bonding electrons, which for nitrogen in this case is 6, minus the number of non-bonding electrons, which is 0. So that's 5 minus 3, that gives you plus 2. So you're going to have plus 2 here on the nitrogen. And then we do the calculation for the oxygen, which would be 6 minus half of 2 minus 6 equal minus 1. So we're going to have minus 1 on each oxygen atom, right? So if you remember what we saw in the previous example, you have atoms that are negatively charged bonded to an atom in the middle, which is positively charged, right? So we know that this will happen. Now, what you might be tempted to do, because you have a plus 2 charge here, you know that this negative charge will cancel out one of these 2 plus charges. You might be tempted to do this to cancel out the other plus charge, right? But that is incorrect. Oops, what's going on? That is incorrect. And I'll tell you the reason why it's incorrect. In fact, we're going to mention this later on. Basically, when it comes to the elements in the periodic table, in periods 1 and 2, those elements cannot have more than 8 electrons on their outer shell in any compound that they form, right? Elements beyond that, 3, 4, etc., can have more than 8 electrons, right? And we're going to see some examples of that later on, all right? But when it comes to elements like nitrogen, oxygen, carbon, those elements cannot have more than 8 electrons on their outer shell. But when it comes to elements below, like phosphorus, sulfur, arsenic, and so on, iodine, bromine, etc., those elements can have more than 8 electrons on their outer shell, all right? So the final answer for this particular question is where this doesn't happen. So the final answer is going to be O double bond N single bond O minus single bond O minus and a plus charge here. And that would be the final answer in terms of the Lewis structure of the nitrogen ion. All right. Okay, any questions about this? Any questions? Any questions? Any questions out there in Zoom? Okay. I take it it's okay for me to clear this, right? Can I clear this? All right. So the next question, let's see if you can do this without my help. Oh, I'm doing the wrong thing. Okay, so the next question is dealing with carbonate ion. So that's CO3, 2 minus. So what's the first step? So carbon will contribute how many? 4. And oxygen will contribute how many? 6. Or we have to multiply by 3. And we have a minus 2 charge here. So what does that mean? We have to add what? 2 electrons, exactly. So this is 18. So 4 plus 18, that's 22 plus 2, so that's 24 electrons, which will be equal to 12 pairs. And then we put the carbon in the middle, surrounded with the oxygens, right? And then we put the bonding pairs first. So 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12. So the next step is to calculate the formal charges. So let's do that for the carbon first, right? So how would you calculate the formal charge for the carbon? What's the group number? 4 minus half of 6 minus 0. So that's 4 minus 3, that's plus 1. So there's a plus 1 charge on the carbon. And then for the oxygen, that would be the group number is 6 minus half of 2 minus 6 equals -1. And that means that each of these will have a -1 charge here. So what's going to happen next? What's going to happen next? Hmm?
But one of the oxygens.
Exactly. Only one oxygen will donate its pair of electrons to form a double bond. So the final answer is going to be this. So this will be the final answer right here. And that's it. All right. Okay, any questions about this? Any questions? Any questions? All right, so as I said before, the other Lewis structures in that question, you should be able to do, but like I said, if you have any issues while doing those, please feel free to contact me below, all right? Okay, let me see, wait, let me go back to the PowerPoint. I mean, not the PowerPoint, the assignment. So, okay, all right, so now we're going to get into a discussion of electronegativity and the polarity of bond, right? So let's first define what we mean by electronegativity, a term that you should have met before in your intro or high school chemistry. Electronegativity is basically a measure of the ability of an atom to attract shared electrons, right? So if you have two atoms that are bonded to each other, right? And if they're different, right? So you have one atom different from the other, then one atom more than likely will have a greater attraction for the shared electron, right? So a guy by the name of Linus Pauling, he basically came up with a way of determining what he called electronegativity values. And basically, it was based on, certain calculations based on ionization energies and electron affinities, right? And basically, according to, he ended up developing he ended up developing a 4-point scale, right? So basically, 4 would be the maximum electronegativity value that a particular atom will have, right? And therefore, the greater the value of the electronegativity, the greater will be the attraction that that atom will have for electrons that are shared. And as far as trends in the periodic table with respect to this particular quantity, what you're going to find is that the electronegativity increases going from left to right and going from bottom to top of any group. All right. So that's basically it. And I think the next slide is a table, right? This table is available in your packet that I've posted in Canvas. You're going to have that to refer to, of course, during your test and so on. All right. So this is basically the table that Linus Pauling developed. And as you can see here, the most electronegative element in the periodic table is fluorine, 4.0, the max, right? You can't have any higher electronegativity value than that, right? And the trends that I described earlier on the previous slide, you can see that here, as you go from left to right, for example, if you look at Puro 2, it starts with lithium, where the value is 1.0, and it just continually increases until you get to fluorine. And that is true right across the board without any exception. And also, as you go from bottom to top of the group, you also have an increase. For example, in in group 1, francium 0.7, and then it increases. Well, actually, it's a general increase. Let's put it that way, because in some cases it doesn't increase from one to the other. Like for example, from francium to cesium, they're about the same. And then it increases to 0.8 for rubidium, and then it stays the same for potassium, and then it increases until you get to hydrogen, right? So that's basically what is observed when it comes to the trends in the electronegativity values, all right? Now, based on what we have just looked at, well, actually, no. Based on the periodic table alone, you're asked to answer these questions. Basically, you're going to order each of these series of elements in terms of increasing electronegativity. In other words, from the smallest to the largest electronegativity value, right? So just based solely on the relative positions of the elements in the periodic table. So in the case of A, we have chlorine, magnesium, and silicon. So according to the periodic table, you're all in the same period. You have magnesium over there in period 3 to the left, and then as you go across, you see silicon, and then you see chlorine at the other end, or almost at the other end. All right, so which one would you place first? Remember now, you're talking about increasing electronegativity. So which one would be the lowest in terms of electronegativity? Magnesium, followed by silicon, followed by chlorine. Very good. What about the next series? You have arsenic, nitrogen, and antimony, Sb. So again, consult the periodic table, and what do we see? We see that they're all in the same group. You have nitrogen at the very top, you have arsenic lower down, and antimony below that, right? So of these three elements, which would be the one with the lowest electronegativity? Antimony, followed by arsenic, followed by nitrogen. Okay, very good. And then the last one, C. Arsenic, selenium, and antimony. Okay, so let's see here. Arsenic is to the left of selenium, and antimony is below arsenic. Okay, so of these three, which would you say would be the one with the lowest electronegativity value? Antimony, followed by arsenic, and then selenium. Okay, very good. All right. So that takes care of that. All right. Now let's talk about, based on what we have just discussed, let's talk about the different types of bonds that we can put in different categories based on the electronegativity value. Now, before we do that, we need to define some different terms here. If you have two identical atoms or two atoms that have the same electronegativity, then when they're bonded to each other, what you'd expect is that the electrons will be shared equally between them, right? So we say that that bond is a non-polar covalent bond. Non-polar covalent bond is a bond where the electrons are shared evenly between the two atoms, right? Now, if you have a situation where there's a significant difference between the electronegativity values, right? Then basically what you'd expect is that the electrons will not be shared evenly. In other words, on average, the electrons will be closer to one atom compared to the other, right? So we called that bond a polar covalent bond, right? A polar covalent bond is one where you have electrons being shared unevenly, such that the electrons on average will spend more time around the more electronegative atom compared to the less electronegative atom, all right? And then we have what are known as ionic bonds. Ionic bonds are basically a very extreme case of polarity. In other words, the difference between the electronegativities of the atoms are so large that basically you don't have sharing of electrons. You have the complete transference of electrons from the metal to the non-metal. So that's what we mean by an ionic bond, right? So the question now becomes, how do we distinguish in a compound the difference between non-polar covalent, polar covalent, and ionic? Well, the criteria that is used in most textbooks is what I'm about to show you, right? And there's this chart here, which basically shows you different types of bonds, and you know whether or not they're ionic, covalent, blah blah blah. So here are the different criteria that we use to establish whether or not a bond is non-polar covalent, polar covalent, or ionic. So, and this is for most intents and purposes, all right? So, if you have two atoms bonded to each other, and the difference in electronegativity values is somewhere between from 0.0 to 0.4, then for most intents and purposes, those bonds are considered to be non-polar covalent, right? So basically, all you need to do is find out the difference in the electronegativity values, which you'll have, you know, in your tables. You find a difference between them, and if the difference is somewhere from 0.0 to 0.4, then the bond is essentially non-polar covalent. And we see some examples here. Now, obviously, and this is true for the vast majority of cases, if you have two identical atoms bonded to each other, that's basically non-polar, right? But you can have some situations where you have two atoms that are bonded to each other, but their values are so close. Like, for example, in the case of chlorine bonded to bromine, the difference between them is 0.2. That falls within that range. So therefore, for most intents and purposes, we can consider that bond to be non-polar covalent. And the same is true in the next example, hydrogen bonded to silicon. In this case here, the difference is 0.3. Again, that bond is considered to be non-polar covalent, right? So basically, for most intents and purposes, if the difference in electronegativities is from 0.0 to 0.4, then we consider those bonds to be non-polar covalent. Now, if the difference is larger, from 0.5 to 1.7, right? Then we say that those bonds are polar covalent, right? So some examples are shown here. For example, the bond between oxygen and chlorine, the difference is 0.5. The same is true for chlorine to carbon, 0.5. And in the case of oxygen to sulfur, it's 1.0. So all of these differences fall within that range from 0.5 to 1.7. So therefore, we say that these bonds are polar covalent. Okay. And then the extreme that I mentioned before, ionic. If the difference between in electronegativity between two atoms that are bonded to each other, if it is 1.8 or greater, right, then basically that bond is an ionic bond, all right? So ionic bonds, of course, are formed when you have the complete transfer of electrons from the metal to the non-metal. So practically speaking, there's no sharing of electrons that is taking place in an ionic bond, all right? Okay. So that's basically the difference between non-polar covalent, polar covalent, and ionic bonds, all right? Okay. And just to give you a pictorial representation of the difference between a polar covalent and a non-polar covalent. In the case of hydrogen, two identical atoms bonded to each other, so therefore you expect the electrons to be shared evenly between them. So therefore the distribution of electrons will be even, as you can see here, a symmetrical arrangement. So therefore that's what happens in the case of a non-polar covalent bond. In the case of an ionic bond, where chlorine is more electronegative than hydrogen, you see that the shape of the electron distribution is not as symmetrical as you see here. And that's because on average, the electrons that are shared will be closer to the chlorine compared to the hydrogen. So therefore, that's why you have this non-symmetrical shape associated with that bond. And below that is a model that is used in chemistry. It's a computer simulation where it's representing the bond that exists between hydrogen and chlorine. And the color scheme for this is that where you see the red region, that means that region is negatively charged, means that it's electron rich. So that's because the electrons are spending more time around the chlorine. And the blue region is basically electron deficient and therefore is positive, right? Now, there are other representations you can use as well to show this sort of polarity of a bond. For example, you may see this, and for those of you who are doing or who will be doing organic chemistry, you're going to see this a lot, right? Basically, this is representing the displacement of the charge from the hydrogen to the chlorine. As a result, the chlorine will be negatively charged and the hydrogen will be positively charged. Now, the charge is not going to be a full negative charge, right? So it won't be a -1 in the case of the chlorine or a +1 in the case of the hydrogen. So that's why we use this symbol here. It's a Greek letter delta, and basically what this represents is that there's a partial negative charge as far as the chlorine is concerned, and a partial positive charge as far as the hydrogen is concerned. No problem. So you'll see this representation, as I said before, especially for those of you, well, you're going to see it here in this course, in some questions later on. But also in organic chemistry, it's very important in organic chemistry that you understand the symbolism. Another representation you can use, which also you see in organic chemistry, is this representation here. This basically shows that the separation of charge resulting from the difference in electronegativity is basically one that is as a directional property, right? And the arrow shows the direction of what we call the polarity of the bond, right? So the convention that is used is that the arrow is pointing from the positive end of the bond to the negative end of the bond. And we put a cross at the tail of that arrow. That's just basically a unique signifier to show that you're representing the direction of the polarity of the bond, all right? So those are just different ways of representing bond polarity, basically, all right? Okay, so let's look at this question. This question says, use the electronegativity values to arrange the following bonds in order of increasing polarity. So again, you're starting from the lowest polarity to the highest polarity. So what you need to do is refer to your table. I think I should have a copy of it here myself. Okay, you need to refer to the table because you're going to need those values for the electronegativity, right? So if you look at the table, okay, in the case of bromine, its value is 2.8. In the case of chlorine, it is 3.0. So the difference between these two is 1.8, right? And then in the case of chlorine, the difference is obviously 0 because they're both identical. In the case of, chlorine to fluorine, chlorine is 3.0 and fluorine is 4.0. So the difference between them would be 1.0. And then in the case of HCl, it's hydrogen is 2.1, chlorine is 3.0. So that will give you 0.9. That's the difference between those two. And then the final one is iodine to chlorine. Okay, so iodine is 5 and chlorine is 3.0. So the difference between them is 5 or 0.5. All right. So basically all we have to do now is arrange them in order of the lowest difference to the highest, right? So obviously the lowest one will be the chlorine, right? And then which one is next in line? The iodine to chlorine. And then the next in line will be HCl. And then the next in line would be Cl to fluorine. And then the one with the greatest electronegativity difference would be the bromine to chlorine bond. And that's it, right? So this would be the order of polarity increasing. All right. Okay, any questions about this? Any questions? Questions? Okay, all right, so let me go back to the assignment. So now you should be able to do question number 3. And again, I'm just going to do the first one and you should be able to do the others. Again, you're going to be needing the table of values here. So what this question is asking for you to do is to basically complete this. First, you need to write down or calculate the electronegativity difference. And then based on the difference, you're going to tell whether or not the bond is either polar covalent, non-polar covalent, or ionic. So for example, in the case of the first one, arsenic, let me look up the value of arsenic. Arsenic has a value of 2.0. And sulfur has a value of 2.5. And you're going to use the absolute value, right? So regardless of the sign, it's going to be positive. So this gives you 0.5. And according to what I showed you, if the difference goes from 0.5 to 1.7, then it is polar covalent. So the answer here would be PC. And that's it. And that's pretty much what you're going to do for the rest of this job, right? So it's very simple. You just find the difference and see if it lies within the ranges for the polar covalent, non-polar covalent, or ionic. And that's basically it. So I'm gonna leave that for you to complete. Again, if you have any issues with completing this, please feel free to contact me about it, all right? Let me see what the next question is asking. Okay, so this question is asking for you to draw the Lewis dot structure for each compound below. And you're gonna label the bonds as either non-polar covalent, polar covalent, or ionic. Again, you're gonna need a table for that. Let me just do the first one for you. So in the case of H2O, the Lewis structure would be HOH with two lone pairs here. And then in terms of the bonds, the electronegativity difference, well, hydrogen is 2.1, oxygen is 3.5. So that difference gives you what? That did 1.4, right? So therefore 1.4 makes it what? Polar covalent, PC. And that's it. All right, and basically, same approach for all the others, all right? Okay, let me see what the next question is. Okay, we won't be able to do that right now. So let me clear this. And let me go to the PowerPoint. Okay, I think this is going to be the last thing we're going to discuss for today's class. So I mentioned, I think, when I first introduced the whole concept of Lewis structures, is that when these atoms are bonded to each other, they try to end up with an octet. But that is not always going to be the case, right? There are some instances where you're not going to end up with 8 electrons, and this is particularly true for the central atom, right? Now, the first type that we're going to deal with where we have that situation is where we have molecules with an odd number of valence electrons. If you have an odd number of valence electrons, you're definitely going to be left with 1 electron unpaired when you put together the Lewis structure, right? So there's a special name given to these molecules. They're called free radicals, right? Free radicals are very reactive because they tend to react in order to obtain another pair of electrons so that they end up with an octet, all right? So that's one type of situation where the molecules will not follow the octet group. Another situation is where you have a molecule where the central atom has what is called an incomplete octet. And what that means basically is that the central atom will have less than 8 electrons. So a good example of this is boron trifluoride. This is the Lewis structure of boron trifluoride here. If you look at the boron atom, you see that it has only 6 electrons or 3 pairs. So it does not have an octet, right? So therefore, that's one example, all right? So that is true for molecules formed from beryllium, boron, and aluminum, right? Again, they tend to be very reactive because again, they try to react so that they end up with an octet. So they try to get electrons from some of that in order to complete that octet, all right? All right, let me erase this here. Okay, and then the next type of molecules that do not obey the octet rule are those molecules where the central atom can, and this is the term that is used, expand their valence shells. And what that means basically is that they can have more than 8 electrons on their outer shell, all right? So that's what happens in some instances that we're going to see shortly. Now, as far as this is concerned, right, we met this before when I was discussing the nitrate ion, the example that we worked, right? Basically, the only elements that can expand their valence are the elements from period 3 and below, right? So if you remember what I said, periods 2 and 1, those elements cannot have more than 8 electrons, right? So therefore, those elements cannot expand their valence shell, right? Elements in periods 3, 4, 5, 6, 7, those elements can expand their valence shell. And some examples are given here, like sulfur, chlorine, and phosphorus, all right? So I think the next slide is a couple of examples where that you're going to observe. So I'm going to start off with the first one, which is BRF5. All right, so we go through the steps as before. Bromine will contribute 7 electrons, chlorine will contribute 7 times 5. So that's equal to 7 5s, 35. So when we add that up, we're going to end up with 42 electrons, which is equal to 21 pairs, right? So we put the bromine in the middle, surround it with the fluorines. And I don't remember if I said this when I introduced Lewis structures, but when it comes to Lewis structures, when it comes to drawing Lewis structures, we are not concerned about the shapes of the molecule, right? All we're concerned about is how the atoms are connected to each other and the different numbers of bonding and non-bonding pairs, right? We're not concerned with the shape. So it doesn't matter how you surround, in this case, how you surround the fluorine around the bromine, all right? So we're going to put the bonding pairs first. 1, 2, 3, 4, 5. Then the non-bonding pairs 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? So we have assigned 20 of the 21 pairs so far. That means that the 21st pair will end up on the bromine, right? And if you look at the structure, you see that obviously bromine has more than 8 electrons on its outer shell, right? So this is one of those examples where bromine is able to expand its valence shell so that you can have more than 8 electrons in that shell, right? So that's basically a very good example of the expanded valence shell situation for bromine. And of course, bromine is in period 4. So based on its position in the periodic table, you can see that that is possible, right? Okay, again, what I'm going to do is leave the others for you to do on your own, right? I think this will be good practice for you guys. Again, if you have any questions or any difficulty while doing these, then again, please see me concerning that, all right? Okay, what time is it? Good time to start. All right, so I'm going to stop here for today. Let me remind you that your test number 3 is on the 25th, which will be next week. Tuesday, all right? And that test will cover chapters 6, 7, and 8. 6, 7, and 8, all right? I'll be here today, of course, for office hours. So if you have any questions, please feel free to come by, or we can link up together on Zoom. I think that's all I have to say by way of announcement, all right? All right, take care.
You're all set.
Oh, yeah, let me just,
No, it's good to go.
oh, that's gonna be good?
Yeah,
Oh, okay.
it's a Dell. So, they actually do, it's like an IO set bit. So
Oh,
what
okay.
happens is you have to unplug it, hit the power button, and then plug it back in and it'll come right up.
Oh, Lord.
Now you know, it's a Dell, man.
All right, thanks.
No, you're good. I'm sorry about the interruption.
Yeah, no problem, no problem. Lordy.
I think you left tests on.
Yeah, I'm very good, yeah. Okay, so leaving Zoom.